Okay, yeah, I'll try and just stay out of it today. Okay. All right, we're on the electrolytic cell. We are skipping the warm-up. Let's go down here to the structure and function of an electrolytic cell. And when you have an electrolyte is going to be a solution that's in water that conducts electricity, and it conducts because you have a molten electrolyte. That means it's melted. That means the ions are freely moving. Or you have an electrolyte solution. Electrolyte solutions have freely moving ions. So when you do the homework problem tonight that asks you which of the following is an electrolyte solution or an electrolyte in a solution, you're looking for substances that have freely moving ions or that can produce freely moving ions when dissolved in water. So this would be called electrolysis, and the apparatus that we're using is an electrolytic cell. I'm going to skip this paragraph at the bottom of the page, and I'm going to go to the top of the next page. Right here. And an electrolytic cell does have some similarities to an electrochemical cell. Oxidation still happens at the anode, and reduction still happens at the cathode. And this is an image of an electrolytic cell here. Some of the differences are we don't have two different compartments. Like we don't have two half cells. We have oxidation, or the anode and the cathode, together in one container, and they're not separated. And then we have a symbol here at the top of the figure. God bless you. This symbol represents an electrochemical cell that has a direct current, because we have to have electricity driving an electrolytic cell because we have a non-spontaneous redox reaction inside of it. So it needs electricity to get it to go. And we have the negative and the positive denoted on this symbol here. And this is showing you where the anode and the cathode are. And then we have the electrons flowing. And then we have our freely moving ions in the solution. The cation is attracted to the cathode. The anion is attracted to the anode. Okay? Electrolytic cells perform the reverse energy transformation. That means we are going to be forcing electrons onto something else. So when we look at the SRP table, it's going to be a little bit different than what you're used to. And in electrolytic cells, the oxidation half-reaction is above the reduction half-reaction. So this right here is something that you should highlight or star. In electrolytic cells, the oxidation half-reaction is above the reduction half-reaction. So electrons will be pushed from the top half-reaction to the bottom half-reaction, and we will use electricity to make that happen. Okay? Typically, the amount of voltage that you need to drive an electrolytic cell is going to be a little bit more than we really need. So this is called overpotential, which is discussed on the next page here at the top. So I'm going to show you how to calculate how much voltage we need using the SRP table. When you calculate the voltage that you need, you're going to get a negative value, as opposed to beforehand with the electrochemical cells, we had positive E values. Here we will have negative E values. Okay? So I'm going to jump straight into the practice problems. So let's take a look here at predicting the voltage required to operate an electrolytic cell. I'm going to do number 1, and then I will have you do number 2. So if I bring up my SRP table here, the half reactions as they are written in this practice problem are the way they will occur in the electrolytic cell, so we don't have to reverse anything. Okay? We just need to find them. So we're looking for silver, which is right here in the SRP table. And then we're looking for nickel, which is underneath it. So nickel's down here. So here's my silver here. And then my nickel is down here. So in electrolytic processes, you're going to be pushing electrons from the top down. So this half reaction here is on top, and this half reaction is on the bottom of the SRP table, okay? The half reaction that's up at the top is the one that gets reversed. So you'll notice they already did that for us. So the electrons are going to be moving in this direction, okay? So we're going to write out the half reactions, make sure the electrons are the same, and then we will calculate the voltage that's needed to drive this process, okay? So if I've got, let me get rid of this table for a second. I've got Ag going to Ag plus and an electron, and then I have nickel plus 2 with 2 electrons going to solid nickel. Now we need to multiply this top reaction by 2 to get the electrons to match. So this would be the overall process that's taking place. And then if you look at the SRP table, you will see that your standard reduction for silver is a positive 0.8, but since this half reaction was reversed, it would be a negative 0.8 volts. And then the other half reaction has a standard reduction potential of 0.26 volts. You will add those two together. You'll end up with negative 1.06 volts, okay? So before with the electrochemical cells, those are positive, these are negative, and this tells you that you need at least 1.06 volts to drive or operate this cell. Okay? Yes?
Why do the electrons go from the top to the bottom?
This is an electrolytic cell, which is different than an electrochemical cell from yesterday. So electrochemical cells had spontaneous redox reactions. These have non-spontaneous. So that means the oxidation half-reaction is going to be up at the top. And you reverse that order of that half-reaction. And then if you had put this much into it, it would actually force those electrons to go to nickel. Okay? Okay, can you guys try number 2? Okay, that's what I got. Good job.
Why do you make the 2.87?
Okay, so let me pull up the SRP table so I can show you. All right, so if you look at where fluorine and copper are, for electrolytic cells, the oxidation half-reaction will be at the top. So you're looking for the one that's up at the top. So that would be this one here, right? And so since the oxidation would be losing electrons and we reverse this half-reaction in the practice problem, you have to put the opposite sign on the reduction potential. So it became negative 2.87. Does that make sense? Yeah? Questions for me before I go on? So I'm just going to summarize electrochemical and electrolytic cells after this. So I'm not going to read through this little paragraph here on comparing electrochemical and electrolytic cells. I'm just going to go straight to the table because it does a really good job of reviewing the differences, okay? So here, with electrochemical cells, which is what we talked about yesterday, they are exothermic and they make electricity. And they have two half cells, right? They're in two different compartments. And they are they operate by a spontaneous redox reaction. And they have a positive E, and they have a salt bridge present. And the oxidation half-reaction is below the reduction half-reaction in the SRP table, so the electrons are moving from the bottom right corner to the top left corner. When we're looking at electrolytic cells, these are endothermic. They require electricity. We have to have some sort of voltage source. We do not have two separate half cells. They have one cell. And then we have a non-spontaneous redox reaction. We have a negative E. We don't have a salt bridge. And the oxidation half-reaction is above the reduction half-reaction in the SRP table, so we force electrons from the top down using electricity, okay? So, based upon this summary, with the person sitting next to you, why don't you take a look at the 7 questions in the quick check, and then we will go over the answers.
For number 2, I'd say it's
That's electrochemical.
no, it's political. Electrolytic.
Well,
It's above. Wait. Number 2, I think is. I just realized it said reduce rather than reduction. Oxidation. That's the point of the salt bridge, it's to connect the ions, so it doesn't leave the circuit up. This is lytic. There's literally one lytic, which doesn't seem right. maybe it is, like, maybe it's meant to be.
You can have both.
You can't.
Yes, for some of them.
Okay.
Two of them, I think, have both. That's the answer.
So maybe both. Just put and electrolytical cells, both. You know, well, I don't know which ones are both yet, but. Well, is it number 3 though?
Yes, you are correct.
Number 6. I feel like it would be let it go because it says it takes to operate. Number 3 is both. Yeah, I was. Okay. I don't second guess myself, I guess. Somehow I did that right. I literally thought I was right.
Okay. How did you do? Pretty okay. Okay. Any questions for me?
How do both of them have like a full circuit for number 5?
The electrons pass through, if you look at the table on the previous page, do you see how the electrical charge is able to pass, like, for instance, the electrons go outside in that wire, and then where the V is, and then the cations travel along that salt bridge to complete the circuit, and then for the other one, again, you've got the electrons traveling outside, like where that DC is, where that wire is, and then you have the cations and the anions migrating towards the electrodes inside that solution. So that's you're completing the circuit. Okay. All right. Can I go on? We're almost done. Believe it or not, we're about to cross out some things. I'm going to talk about electrolytic cell types, and then we're going to cross out some stuff underneath it. There are 3 types of electrolytic cells. Type 1 have inert electrodes. This would be things like carbon electrodes or platinum electrodes. And they're going to be immersed in a molten ionic compound. That means that's melted, and you have freely moving ions. And only the molten ions can be oxidized and reduced. That means one thing can be oxidized and reduced. If you're looking at a type 2 electrolytic cell, they also have inert electrodes immersed in an aqueous ionic solution, so that means it's dissolved in water. And then only the ions or water can be oxidized or reduced. That means 2 things can be oxidized and reduced. In type 3 cells, you would have non-inert electrodes. These would be something like a magnesium electrode, and they're going to be immersed in aqueous ionic solution, and the ions, water, or the anode can be oxidized, and the ions or water can be reduced. That means you have 3 things that can be oxidized and reduced. I'm not going to go over more of the details on type 1 or type 2 cells, so I'm skipping over that. We're skipping over these 2 sample problems, and I'm going to go straight to the practice problems here. So take a look at question number 1. We're going to identify the type of electrolytic cell. We're not going to do the half reactions occurring within it. So if we're looking at A and we have carbon electrodes in magnesium iodide. So since this says it's liquid, this means it's molten. Are carbon electrodes inert? Yes. So what type would this be? Type 1. Okay, let's go to letter B. Platinum electrodes in a calcium sulfate solution. So platinum electrodes are inert, and then your calcium sulfate solution, this would be an aqueous ionic solution. So this would be type, correct, type 2. And then for letter C, we've got iron electrodes. Those are not inert. And then you have sodium chloride dissolved in water. This is an aqueous ionic solution. Type 3. Okay. Question.
How can you tell if one's inert or
I told you that on the notes in the previous page. Inert electrodes would be carbon and platinum.
not? Oh, okay.
Okay. And basically everything else would be non-inert for you. Okay. Let's go to number 2. Let's draw an electrolytic cell that has carbon electrodes in a nickel 2 bromide solution, and then we'll label the parts. So for this one, you're going to have just one compartment. And within it, you've got 2 carbon electrodes. And then they're in a nickel 2 bromide solution, so I'm just putting a nickel 2 ion and a bromide ion. And then you have a DC source, so remember that looks like this. And then has a negative and a positive. And then they want you to label the anode and the cathode. Anode, cathode. Electrons flow in this direction. And then your cations are going to be attracted to the cathode, and the anions are attracted to the anode. And then they want the half reactions that are happening. Well, since bromine is the one that's losing the electrons, if you look at the SRP table, this would be the half reaction for bromine. And then the corresponding E value is negative 1.09 volts. And then your nickel is accepting the electrons, and that corresponding E value is negative 0.26 volts. So you'll add these two together. And you're going to get negative 1.35 volts. So this means that a voltage of at least 1.35 is required to operate the cell. All right, God bless you. Okay, on the next page, we have some applications of electrolytic cells. I'm just going to talk about 3 things: electrowinning, electroplating, and electrorefining, and everything else you're going to be crossing out. So if you turn to here, electrolytic cells are used in mining, and electrowinning is where we recover a metal from a solution that contains its ions. So the ions would be combining with the electrons, so they would get reduced, and then you would end up depositing metal. Electroplating is a form of electrowinning. It's where we have a metal coated with a thin layer of a different metal, and this protects it from corrosion. This happens with your bathroom fixtures and automobile parts. Bless you. Electrorefining is another application of electrowinning. That's the electrolytic purification of metal. So we end up having a metal of an impure anode, and it gets oxidized to its ions, and then those ions are going to migrate to the pure cathode, and they get reduced back to the metal. And that leaves all the impurities behind. You can go ahead and cross out applications down here at the bottom of the page. You can also cross out the next page, the two other application examples. And your homework questions are 1, 2, 6, 7, 11.
Let's see.